approximations or discrete schemes can be rewritten into continuous ones, and sometimes it is good to do that. So that is what we have seen in case of finite difference schemes, that it was better to consider the finite difference scheme in the whole space, not on the grid, and then one can work with the theory of SPDEs, not just with the finite difference schemes. A similar situation can be a similar approach, that is embedding the scheme into continuous one. The discrete scheme of the continuous one may appear in other situations. So now I would like to consider splitting up schemes, that is discretizing in time, and there again the approach will be to embed that into a continuous time scheme. So what I am talking today can be found in more details and with more generality in these papers. I also wrote slides about the lecture, which I originally wanted to project, and then it would be quicker, but I think it's better if I explain, and I am also working on the slides, but those will be available. So, what we consider the following equation, SPD, linear, so always the same. What we consider with somewhat more generality this time. The operator on the right hand side is written in as sum of operators. So here are from 1 to D2, LR UT plus FR DT. So the title is Splitting Up Methods for SPDs. And this is the ST we consider, so this dt, then plus L naught ut plus f naught dt plus n rho ut plus g rho dwt with an initial condition. And now I should be careful to write the time always here in parentheses, because I will have many indices. So with an initial condition. And so notice that here we have sum of operators and free terms. And here let us consider this one as one block, and assume that because of some reason we have good methods for solving the equation. I write it with solving du, and here the not is an index, not the initial condition, equals L naught ut plus f naught plus m rho u naught t 0 dwt. This is equation with index 0. And the du, and I use r, lr ur t plus fr plus, and that's it, dt. Here I lost the dt.
And plus in front of g.
and plus in front of g, thank you. And here the dt. Here we have, this is the equation with index r, and let's say, or we know here, r is running from 1 to d2, rho as usual, the index running through 1 to d1. And so suppose that these equations with good initial conditions can be solved well, and then the aim is to get the solution of the main equation by solving these equations on small intervals and switching all the time. So this is the splitting up method. More precisely, suppose that, let us just for the presentation consider the time-independent case. So suppose that the coefficients of LR, L naught, and rho, these are, so the first ones with L, these are second-order differential operators as usual in these lectures, and M rho is first-order operator, right? And suppose that suppose that those are independent of time, and also the free terms are independent of time, to have a simple presentation. So in the time independent operators and free terms for now, and assume that this is solvable from any good initial condition. Then let us denote by Q S T psi the solution to the zero equation at time t, when the initial condition is psi at time s. So s is less than or equal to t. I just introduced this notation to explain maybe easier, or at least write down the splitting up method in this situation, and let s t psi denote then r with an r, here an index r, denote the solution to equation with index r at time t with initial condition psi at 0, because this is a time independent equation, right? When we want to write that the similar thing, that initial condition at time s is psi, that is just the same as SR t minus psi, so it's enough to use this. Oh, right. Okay. And then the splitting up method is the following, that we let us fix the zero capital T interval and then take equidistant points here. So the grid here is denoted by Tn. N is a fixed integer, and the Tn is I times tau. I is from 0 to n, and the tau is, so the mesh is the T over n. And so suppose here is the Ti point, this is the Ti point, and the Ti plus 1. Then recursively we can describe the method like this, that the let u, here the n corresponds to this n, and let this denote this the approximation by splitting up method, then recursively this is given like this, that at the next time point we get it by taking the value at the TI point, taking the solution at the TI point. Then we use, let's say, first the equation which is the zero with the zero, so that has the Q solution operator, so that is taken from TI to TI plus 1. So that means here with the initial, taking as an initial condition what we got at the TI point, we solve the equation with label 0 first, then we go to the other equations and solve, so that is S1 and tau and so on, S, and here we have the too many tau. So once again, first we solve with the 0, and then we arrive to this. Then we got a value at TI plus 1. We take that as an initial condition for the next equation, solve with that initial condition, and then again what we get we use as an initial condition for the next, and so on. So we run through all the equations, and so this is how we get so this is for I from 0 and so on, n minus 1, and at 0 we start with the initial condition, right? So this is, yeah.
If you look at the notation QST, I think you don't need to put order, you don't need to put UNTI. Just I think it's just UN, just UN. In fact, no. Yes, but I want to express that so I want to construct an approximation UN T for T from the time grid, yes, and then in order to do that, to define, I should take so okay, when I am at the 0 time, so when I equals 0, then I take the initial condition, solving, so then this is psi, but then the next time I should take the UNT1 and start with that as an initial condition, solve with this initial condition, and then take it again back as an initial condition at the time point. So always solving with one equation, then we get a value that we take back, and with that initial condition we solve the problem with the other equation, then we take that back, and then this is how the process is described. Is it all right? So I would keep this notation as I have written. Okay, so this is a oops, sorry.
Okay, so just a question that how can we see that one is really good approximation? I mean, is it an intuitive explanation for this?
Why we think that this is a good approximation intuitively, because this is just we obviously we
we have to solve with orders. So these are present, these operators everywhere. Now we think if we solve it on separately, only on small intervals, one after the others, then it doesn't make much change. In fact, the other application, the other way is well, maybe I won't go to explain why this is for me somehow intuitively clear, and we will prove it that even rate of convergence. Maybe the other way how people know that is already from Trotter formula. People know that the solution. So in the linear case, so it is a well-known fact, and also in the deterministic case, a well-studied approximation for ODEs and also for PDEs in the deterministic case. So there are many works, and in these works mostly the semi-group method is used. So in the deterministic case we don't have this one here, so we have this product of so in case, for example, if we don't have the free terms, then we have the product of these semi-groups at T, and then by Trotter theorem one can show that there is a convergence. Maybe I will give later Trotter's theorem formulation. And also one can study the rate of convergence, and that was done. And in these papers a new method is shown that instead of using the semi-group method, it is better to, or it is convenient to embed this method into continuous time. So instead of going back and forth, as the splitting approximation is organized in time, let us rearrange in forward time this method and write down the approximation, or embed. The approximation is defined at the discrete points, but let us embed it into a continuous time, and then we can use methods from PDEs to compare the true solution and the splitting up method. So this is what we are going to do now.
I still don't understand your notation. USRT. So starting point is 0, right? So
The start here, starting point, the time is 0 here.
in that case, you already used of the TI, that in the next step is treat like between 0 and first step.
I could have written it also further, that now instead of this, ti plus 1, so introduce here 2 parameters like here, right? But because this I want to present the time-independent case, so therefore I can write it with 1 parameter, yes? That if I introduce, is that your question? So if I could introduce that similarly, that ST denotes the solution of equation, so with R at time t, when the initial condition at time s is psi. But because of the time invariance, that is time independence, sorry, that can be written by just 1 parameter, yes, so only the t minus s plays a role, so that is the tau. Have I introduced the tau? Yes, that is the tau, so therefore I have written it like this.
In that case, it's more like you just evaluate at 0, not TI. Because you just put it back.
But on the next step, UTI is the initial value.
Yeah. So,
If you write, say, UN1 instead of TI.
Yeah.
You would take UN1 as initial value. That's not that's mathematical. You want to take what you got on the step leading to TI. And then this is your initial value.
So once again, we start from 0, initial condition, so with psi. Then in order to get our approximation at the point T1, we solve first, let's say, the 0 equation with initial condition psi, and we arrive at time T1. Then, as a new initial condition, we take this back and we solve again so many times, as many equations we have, but we always, what we got, we take it back as an initial condition at the previous time and solve the next and so on, right? This is and I wanted to write here recursively what we are doing. Okay, so then the idea, let us just, maybe I formulate first the theorem, and then I explain the proof. So what we got in the time-independent case is this theorem.
Professor change, we're going to change the marker because
Oops, I haven't put back somewhere. Not now. Take another one.
Yes.
Yeah, thank you. My Russian seems to be better than my English. And Hungarian is not available, I'm afraid, which is even better, I hope. Yeah. So, theorem. So again, I call it theorem 1 as the. So we. Not good? Not good enough. So as always, LR is a second order, but now I write it in this form: AIJR DIJ plus AIR and DI plus AR, and summation with respect to IJ. I is running from 1 to D only now, and the R stands for the operator LR. So R is from 1 to D2, and so this is just what we have. And yes, we have only one M, but the rho is the coordinate. So this is BI rho DI plus B rho. And okay, and now the assumptions. So assumption 1 is about the regularity of the coefficients. So we take as usual, we fix an M greater than or equal to 0, and define this like as follows, that these coefficients, and so all the coefficients here and their derivatives up to M are continuous functions and bounded by a constant, bounded BDB by a constant C. Don't forget, we consider time independent case, so we don't have dependence on time. So
also then no dependence on omega, or if we have dependence, then only F naught measurability, which is just the same as no dependence on omega, so just time independent case so far. Then second, for the three terms that F are in the M norm, so we have M norm less than or equal to C, and then the G M plus 1 norm less than or equal to C, and the U initial condition. Oops, I cannot use this U not anymore because there will be a confusion. So our initial condition is psi is also in M less than or equal than constant C. And third, that we have the that the matrices or the operators L are degenerate elliptic. So I write it like this, that this matrix for each R is non-negative definite, and the degenerate stochastic parabolicity condition for the in fact here the R is running from 1 to D2, then I describe these ones, but here there is also a 0, so I should add also that one, and here R runs from 0 to D2, so I should include the coefficients of the R naught and operator as well. And for this equation, so for the equation with label 0, one should, for the solvability, assume the parabolicity, stochastic parabolicity condition. We weaken a little bit because it turns out that finally we have to deal with degenerate equations anyway in our method. So here the assumption is that ij minus 1/2 and then bi rho bj rho, this matrix is non-degenerate. Right? So instead of writing that kappa times the identity matrix is somewhat weaker, and so we should know solvability of that, and I will give that what we will use. So all right, so this is these are the assumptions, and then the theorem says that so again theorem 1 says that if we have 1, 2, 3 through 3 with m greater than or equal than a fixed L integer plus 4 or some L integer non-negative, then we have the following estimates for the, so first of all the UN approximation is well defined, so we can solve all those equations which we want, and the estimate is UN t minus ut, so u is the original, in the L norm squared, and maximum over t expectation is less than or equal than a fixed constant times h tau. We have tau here,
tau squared for all n, where small n, where capital N is a constant depending only on the dimension. So we are in Rd, also on L, then the D1 number of, so the dimensionality of the linear process, D2, how many operators we have, and then the fixed time we consider. Right, so this is the theorem, what we are going to prove, and so I think I can get rid of this part, and then the idea of the proof. So let's see first here.
I have a question.
Yeah.
So the condition 3 actually allows us to have degenerate somewhere, the diffusion by degenerate somewhere.
Yeah. So
Here you can mean that there is a solvability already.
questionable, right? Or is that?
So do we know that the solution does in this case?
Yes. So we don't know enough, in fact, still to use what I am doing now. So I will formulate precisely what we need for the solvability of these equations. So we need a theorem on existence uniqueness for SPDEs with the degenerate parabolicity, stochastic parabolicity condition instead of the parabolicity, and I will formulate that and maybe some words about how to get that result. Yes, because we always so far assume the stochastic parabolicity and not a weaker condition. So the proof, the main steps I would like to show. So first of all, that for each, so under these conditions, for each R, D2, the equation with label R has a solution if we assume that the initial condition satisfies the second condition, that it is in L plus 4, so we have space, yes, L plus 4 for the initial condition as well. In that case, each equation has a solution, and moreover, it has a unique solution, Moreover, that this unique solution is weakly continuous, or maybe I write it like this, that L plus, so M, I write HM valued, weakly continuous, process. In fact, it is HM minus 1 valued, strongly continuous. Strongly continuous. That I just say without referring yet, so I will formulate, so C, theorem 2, later in this talk, which I don't want to formulate twice, because we will need that result again the main step, so therefore I don't want to formulate. So there is a theorem about solvability of SPDs when we have the degenerates, and that theorem will be formulated and used. And by that theorem we have the solution, so we can talk about the approximation and also the original one. Now the question how to deal with this approximation, that instead of going back and forth in time to rearrange. So now the idea is this is the main idea that rearrange in forward time. So rewrite this method in forward time. Rewrite in forward time, and also a synchronization in time, you will see. So to describe this, let us consider time scales, which does the job for us to rewrite in forward time. So for simplicity, let us consider the case when D2 is only 1. Just not to have too many time scales to write. D2 only 1 means that we have two equations and we switch between them. So not more, just only two. And to describe the method, we consider the following time transformation or time scale. Let us consider tau 2 tau, and on this take the following time scale function until tau, it's the usual time. Then we stop doing. The time is nothing is happening. The time is going, but nothing will happen when we and then again. So we consider a periodic the derivative. So let us denote this by kappa, and the kappa dot, which is the derivative, is periodic function. On the 0 tau it is 1, and then on tau 2 tau it is 0 and periodic with period with period 2 tau, and let us consider another scaling, which is then the kappa t minus also for the sake of notation is let us consider it 0 in the past, 0 when t is less than or equal 0, and another one is we consider other scaling, which is the kappa t minus tau, and that is then like this. So when this is growing, it remains 0, and then it starts while this doesn't do anything, or a constant, and so on. So again, now how we use this, that we stretch out the time twice as long, and then when we solve the equation, the first equation on this interval, then we consider it solved by this scale described that we will not do anything until that. Then we stop solving the the first equation, and then we solve that one. How to write this down? We also need to use the time change of the VNet process, so that is yt, which is the w, and with this kappa t, we change the time, so this is our kappa kappa t. Similarly, we have to change the corresponding filtration, right, and then the approximation is written like this. That is V1 is related to describing the approximation, and its equation is dv1t, and then I explain, is sorry, I use sorry, not V1, I use the U in my notes, so let me use that one. So U1t is L naught U1 plus F naught dV naught, where that is just another notation to have some unified later. So this one is the kappa t, so dv naught t plus the mu1 plus g. The u1 is just an index, and I don't write the argument t, and here dyt plus the L u1 plus f1 dv1t, and so this is the v1t, the other, the red one, here is the v1t.
I just want to make sure that kappa t is 2 period, which means it's starting from 2 tau, the same shaping again.
Starting from 0
and shape like this.
Until time tau, it is just the ordinary time. As the time is going, this is just the same. Then it stops growing until 2 tau, and then it goes up again and so on. So maybe I write it with the formula as well.
Kappa prime period. Okay.
The kappa prime, I haven't written that. Yes, sorry. Periodic was two. Maybe I just write down then the kappa t itself, just to have this one formula. That is, then if we see this definition, that it will be k times 2 tau if t is in the 2k tau, 2k plus 1 tau interval for k 0, 1 and so on. It stands at k plus 1 t constant when t is in the 2k plus 1 times tau and 2k plus 2 tau interval, and 0 when t is less than or equal. So I have written down just by formulas the function, which is just written. Right, and so the v1 is the other. So let's see what does this do. So
when we consider the zero, we consider the thing on the 0 tau interval, what is happening, then that means we solve the equation with label, we solve the equation with label 0 until this. Why? Because this is just 0. The V1t is just the differential of it is 0. It is a constant, so nothing happening. We are waiting tau time to solve the other one, right? And then from tau to 2 tau in the other way around, nothing happening here, and we solve the other equation. So you see, in this way we rearrange the method in forward time by stretching out the time scale. Now we should also synchronize to this the original equation, so therefore we write that for the original equation that has the synchronized version of u is denoted by u naught. This is not the initial condition. Therefore I write the t always here. So for that we write this is then the L t plus f v 0 t plus m u naught t plus g d y t. So what happens? What does this synchronization means? That we solve the original equation here, but not exactly, because so what happens is that until tau, this is just the same equation, just the original equation, right? This because until tau the kappa t is just a t, so we solve the original equation until tau, but then we stop solving because the as we this is a constant then on the tau 2 tau, so we stop solving and then again we start and so on. So this is then synchronize this one to that in which way? That what can we say? That the u and t, the approximation, the splitting up approximation, is the same as u1 2t at the point t from the tau n. Notice that the u and t is not defined anywhere else, but in this way we embed it into continuous time, and there is a good relation. So this one, that in fact these are equal at the point of the grids, and similarly the ut equals u not 2t, so we synchronize with this 2t again when t is from the right. So and because of this, if we want to estimate the difference in any norm, so for example in the L norm, and take the
maximum over the grid, then that is less than or equal, then if we take the supremum, now t less than or equal than 2 capital T, we have to stretch twice, and then u 1t minus u not t in the same norm. So this is what we use. So now we have two equations, one for the related to the approximation, another one which is related in those ways to the original equation, and then we should consider the difference, and from the difference we have to estimate. We write down again an equation for the difference from the two with an obvious way, and then solving that equation we get the estimate. So this is one way to do it. But let me write down once again this equation to have it in a more suitable way, because do not forget that in fact this L is the sum, right, of L naught and L1. So therefore, instead of this, I write it like that: LR U naught T plus FR, and then I write dVR, right? But not to have a confusion here, I just make some adjustment, just a minute, because this is not correct yet, according to my notation. And then to add another index, 0, here 1, to express that this one corresponds to the U1, and so this here is also, this one is denoted by V11, to have that index, to keep in mind that this one belongs to the approximation equation. And here I put a 0, and V0 with any R is just the same as the kappa. In this way, I have written down the equation for U naught in a very similar way as it is written here. So maybe
Sorry?
Oops.
The last line, you have to add L0 operator.
In the last line,
It will be the original
values for your series.
L0.
you mean in this equation?
Yes.
In this equation, I have also, by this way, the L0, and this is why I introduced this, that you see the WR0 for R equals 1, 0 is just the same, the kappa, so in this way it is summed up, right? So I split it here just accordingly how it is splitted in there. So just a convenient notation to write the two equations in a very similar way. So I repeat now then once again the two equations here to work with. So the du1 t is LR U1T plus FR and dV1R, right, plus MU1 plus G dyT, and du0 T is similarly, but with u0 T plus FR, and dVR and 1, not 1 but 0, sorry, this corresponds to that one, so 0 plus the MU0 plus G dyT. So these are the two equations, and you see, in case we have more, so multi-stage, many equations, not just two, then the similar thing is done, but then instead of V1 we will have VR, and that is the kappa T minus, and let's R times tau. So then instead of having two periodic one, we will have D2 plus 1 periodic one, and then here in that case the summation is running through all those in R. So just a similar way. Okay, so suppose we understood that in this way we really describe the approximation by using this according to a time scale on at the grid points, and this one as well, so that we want to compare the solutions of these two. Notice it is important that the driving martingale, this is a martingale, we just changed the Wiener process in this way. The driving martingales are the same at the two processes. The only difference, so these the first terms, I mean the operators there are also the same, but only difference that the driving processes here are different. But it is natural to expect that the difference between the two in any reasonable norm must be estimated, expectation and so on, must be estimated by the differences, the maximum differences of these ones. Yes, this is the only difference between the two equations. So the driving process, so what we expect here, that then let us call this a let's say on now we have on a t, should consider on the t prime, which is in this case 2t interval, or in the general case the d2 plus 1 times t interval, but let us forget the prime, just our aim now is to solve, and so the aim is to compare the solutions as on any time, so more precisely t prime, but I will forget it. So this must be estimated by A, which is the maximum over whole R and the supremum of the V R1 minus VR0, and we will see that this is indeed the case, that the solution in this norm will be estimated by constant times and this this one. So this is what we are going to show now. Now we have only 10 minutes. And let us start one simple method how to compare the solutions of these two. There are better methods as well, but this is a simple method which will work. And so we take the difference, and so we want an equation as usual for the difference, which is u1t minus u0 t, and let me write down the equation for this. dvt, just subtracting the two, but a little bit of rewriting. lr vt dv1 rt plus mvt dyt and plus lr u0 t plus fr, and here we write the difference between the driving increasing processes. Which in fact, okay, I denote this one by ART. So I think I haven't made that. That's a very simple calculation. So we subtract, but first, instead of the V0 R, we imagine we write V1 R, right? In that case, the F are cancelled. LR times the U1 minus U0 is the V1R, but then we should compensate, right? Instead of this, then the additional term to compensate this is the LR U0 T plus FR times the difference between the V0, yes, this is the true thing here, minus the V. So far, this is a very simple calculation, and it is true. Now we introduce the WT, not the Wiener process, this must be small WT, which is defined as the VT. This is the back term here for us. This looks like a nice equation, right? But this is a bad term, not a good free term. So we want to get rid of it, and the way is that we introduce the WT, VT minus the product of these LR U0 T plus FR times the ART. And write the equation for the WT. What is that? Then we have that it is, maybe I don't write that easy calculation, and I just write the result that what is this based on, that we should take the differential of this. For dVt, we know what is the differential, it is written here. Then we should take the differential of this product. We rigorously can show that that is this one times the differential ART, yes, plus the differential plus ART times the differential of this one. So one should write down the differential of that one. The one where we have the DART is just cancels this term. So therefore it is really a simple calculation, and then we get LR WT plus F1 F1R, and here that was the ART, and here the D and V1 RT, so just the same thing there, plus the FJ naught DV naught JT plus MWT plus GDYT, where the F1 with index R is L operator with index R, LJ, U naught plus FJ, and RAT with upper index J. So this is a multiplication. Then we need to write the FJ0. This is minus TR LR LJ U naught plus FJ, and finally the G. Oops, that is a bit longer. So the G is we already know this equation. The G is M LR minus LRM. So this is a commutator, U naught times the AR, and plus the M on FR plus LR G times the A strange that why I wrote the AJ here, must be here also, and summation, not the J but the R, the R. And so what we have done, we made this we have written, as we discussed, we took the differential, so that part is killed, but we have other coming the differentials of this one, so that means we take the differential of U naught. This is why here such term appears, right? LR, and then the differential of U naught is this one. It is multiplied by the A, but also such term must appear with the Y as well at the G. So this is when M and then LR, right, and then the dy. What else we have done is that instead of V, because we want an equation for the W, instead of V we write, yes, instead of V from here we write that is WT plus this business. So this is how the other terms appear. So believe me, I think I haven't made mistakes here. That then the three terms are as it is written here, and I think I have to stop here, and then next time I formulate
a theorem which is about the solvability of such an equation and the estimate for that, and from that theorem we directly get the necessary estimate for the W, and that theorem also contains the solvability results and uniqueness about the degenerate SPDs. So that is the, yeah. So to separate the equation such that just the stochastic term to have it alone, yes, that is separating would be when we see that there is this part that M rho, or just M and U plus the G, and then D W T, then let us consider such an equation separately, which is the du with some r equals the mu plus g dw wt as mu r, but this one is not solvable, because you know that we need, for solvability, Professor Klopp showed us that we need the stochastic parabolicity or the degenerate, and here this is not solvable. We don't have that condition. We have only the noise, nothing to help to solve it. So this is why there is in that with zero, let's say with the zero, we took also part this L naught U naught plus F dt, in order the L naught could help that equation to be solvable. So one cannot separate in this case just the stochastic part. One should add something which helps. If one introduces the Stratonovich version, so if then here is to write the Stratonovich version, which I am not going to do now, that is just gives, okay, that gives that adds the 1/2 m squared u m squared u. Let us not so m, what does that exactly do? M, and then m u plus g, and I, or yes, rho, and then dt plus the m u plus g with this dwt. This makes just solvable. So then, for example, one can add for L, to have it for the L naught, the m squared operator, and with 1/2, and then that gives already the solvability of that. So anyway, the answer to this question that there must be a second order operator if we write it in the Ito form in order to have that equation to be solvable.